We write lines of code every single day, right? But have you ever really stopped and thought about what's actually happening under the hood the moment you type that semicolon? Well, today, we're going to pull back the curtain and look at the secret life of a single line of code.
So, just look at this line of code. Seems pretty simple, doesn't it? We write stuff like this all the time. But to the compiler, this isn't just a line of text. Oh no, it's a detailed set of instructions. It's a puzzle that it needs to solve, piece by piece. So come on, let's pop the hood and see what's really going on in there.
All right, we're going to follow this little line of code on a journey, but we're going to do it from a really cool perspective. We're going to see it through the eyes of the compiler itself. What does it notice first? What steps does it take? Let's dive in.
Okay, so the very first stop on our journey is all about the numbers. Before the compiler can do anything else, it has to look at the math we've written and just make sense of it all.
So first things first, the compiler zones in on the calculation. See this part right here, x times 2.5? That's what we call an arithmetic expression. It's pretty simple. You've got your operands, the things being worked on, like the variable x and the number 2.5, and then you have your operator, in this case, the multiplication sign. The compiler's first job is just to turn this whole thing into one single number.
And this is where the compiler starts to show off how smart it is. It sees an operator, like the plus sign in our example. Now, as you can see here, if it sees that plus between two integers, it knows, okay, I need to do addition. But if it sees that exact same symbol between two strings of text, it knows to join them together. This is called operator overloading. The same symbol has different meanings depending on the context. The compiler has to be a bit of a detective here and figure out the right job to do every single time.
Which, leads to a great question. If we go back to our original line of code, let's say x is an integer, but we're multiplying it by 2.5, which is a floating point number. Those are two different data types. So how does the compiler handle a mismatch like that?
Well, it does something really clever called implicit type conversion. Honestly, the best way to think about it is with money. You can't just do a transaction with both rupees and dollars at the same time, right? You have to convert one of them first. The compiler does the exact same thing. It sees that the int is a smaller type than the float. So to avoid losing any precision, it temporarily promotes the integer to a float. Now it's just multiplying two floats together, no problem, and no data gets lost. And the best part? This all happens automatically, behind the scenes.
Okay, so the compiler has figured out all the math, but our code isn't just about crunching numbers, it's about making decisions. And that brings us to the next stop on our journey, the world of logic. This is the real heart of how our programs make choices.
And this is all handled using what we call relational and Boolean expressions. Now, unlike the arithmetic expressions that give you a number, these expressions give you a much simpler answer. It's either true or it's false. That's it. This simple binary outcome is the foundation for every single if statement, every while loop, basically any decision your code ever has to make. And here are the tools the compiler uses for that. You've got your relational operators, things like is equal to or is greater than, that compare two values. And then you have the really powerful ones, the Boolean operators like and or. These let you chain multiple questions together to ask really complex things like, hey, is A greater than 10 and is B less than 5? This is how you start to build some real intelligence into your programs.
All right, for our third stop, we're going to look at one of the cleverest tricks a compiler has up its sleeve. It's all about one simple principle: work smarter, not harder.
Let me just ask you this. Just think about it logically for a second. If you're checking an AND condition where both A and B have to be true for the whole thing to be true, and you check A and find out it's false, is there any point at all in even looking at B?
Right? Of course not. The whole thing is already guaranteed to be false. And the compiler is smart enough to know this. It's a technique called short-circuit evaluation. For an AND statement, if the first part is false, the compiler just stops right there. It doesn't even bother looking at the second part. Now, this saves processing time, sure, but it's also an amazing tool for preventing bugs. Think about checking something like if user equals null and user.isLoggedIn. If that user object is null, it stops immediately. It never tries to call the isLoggedIn function on a null object, which would crash your program. It's a beautifully efficient and safe design.
And that brings us to the final stop on our little journey. After all the math has been done, all the logic has been checked, there's just one last job to do: store the final result. This is where the assignment statement comes into play, and it is so crucial to understand this. In most programming languages, that single equal sign isn't asking a question. It's not checking for equality. No, it's a command. It is an order. It says, take whatever the final value is on the right side, and you will store it in the memory location, the box, labeled with a variable name on the left.
But what happens if the types don't match here either? For instance, what if we've calculated a floating point value, like 7.5, but we're trying to assign it to a variable that's an integer, like count? We call this a mixed mode assignment.
Now here is the absolutely critical part to remember. The compiler will force the value on the right to fit into the variable type on the left. So 7.5 has to become an integer. But be careful, it doesn't round up to 8. It truncates. That means it literally just chops off everything after the decimal point. The 0.5 is gone forever. This kind of unexpected data loss is a classic source of really tricky, hard-to-find bugs, so it's a super important one to keep in mind.
So there you have it, the complete 4-part journey of a single line of code, all from the compiler's point of view. It decodes the math, deals with different types, it evaluates logic, it works efficiently with smart shortcuts, and finally it assigns that final result into memory. It's this incredible little process that happens in the blink of an eye millions of times over.
So the next time you write even the simplest line of code, I want you to remember this journey. Because knowing about things like type conversion and short-circuiting, that isn't just trivia. It can make you a more intentional, more deliberate, and a much more effective programmer. Will you think twice now before you mix data types? Or maybe structure your if statements just a little bit differently to be more efficient? I really hope this peek behind the curtain was helpful. Thanks for tuning in.